right, hi everybody. Thanks for showing up. We've got lots of people in the room. I guess I should do Saturday demos more often. We're just going to start by recapping a little bit of stuff from last time and correcting it. We had a little bit of a performance demo last time, and one of the numbers was wrong, so we'll correct that. And then we're going to talk about some smaller features and then lead into some bigger features. All right, so last time in the performance demo, I was talking about compiling this demo program. It was 33,000 lines of code, and it was on this particular Razor Blade computer and all that, right? So we went into great detail last time. It was just a recap. But I was reporting how fast the LLVM backend was versus the x64 backend that I had programmed that was made to go as quickly as possible just by emitting x64 instructions with absolutely no optimization, right? And these are the numbers that I reported. So 0.88 seconds totally for the backend, or no, 0.88 seconds for the entire compile. So compiling in less than 1 second. And the LLVM backend, which is us feeding LLVM our data plus LLVM processing our data, and then handing that off to the Microsoft linker took about 0.7 seconds, 0.69. And then the actual LLVM part without the Microsoft linker was like 0.47, right? Those numbers were a bank error in LLVM's favor because I had not paid enough attention to the commits, and it turns out that Josh, who did the LLVM work, as well as doing operating system portability work and stuff now. Josh had multi-threaded the LLVM backend, and these numbers are actually these are real numbers. These are the real times, but they are the times for 4 threads compiling LLVM in parallel. And I didn't realize that. And then someone who we're corresponding with on email said, "How did you get LLVM to go so fast? For 33,000 line program?" And I was like, "Well, we did these optimizations." And I was like, actually it is pretty fast. And Josh was like, "Oh yeah, we parallelized it." So whereas these numbers are correct for that hardware, is not an apples to apples comparison versus our backend, our x64 backend, which could be parallelized, but we haven't bothered yet because it's so fast, right? So if you're going to do apples to apples, you want to sort of compare the single-threaded LLVM speed versus the single-threaded x64 backend. So here's our numbers for single-threaded for 4 threads on this laptop, which has 4 physical cores. Maybe we should try 8 threads or whatever, but we're not being that serious about it. But it takes almost twice as long single-threaded. It takes 1.6 seconds to compile the whole thing. 1.45. Remember, our front end is like 0.18 seconds, right? So most of that time is in the back end, 1.45 seconds. Here's what we reported last time, these numbers on the left for LLVM. We've now noted that that's multi-threaded for X. We got about a 2 times speed up from having 4 threads, right? It's often, we haven't necessarily been super serious about the parallelization, which is why we're only getting a 2 times speed up. But, it's hard to get a 4 times speed up out of 4 threads if you're doing anything that has a little bit of data communication in it. So that's not too surprising. So here's our single-threaded numbers, right? And here's the x64 numbers. These are the same as what we reported last time. So you can see, actually, this middle column is much higher than it was. So here's the speed ups we reported last time. We said we were 4.6x faster than LLVM if you count linking, which we're both basically waiting for the Microsoft linker to do its work, and without linking, 16 times faster. Those numbers are actual underestimates, right? So if it's an apples to apples comparison of single-threaded versus single-threaded, then we actually did about twice as good as I reported, right? So if we're waiting for the linker and counting that, we get about a 9.7, almost 10x speed up over the LLVM backend. And if you're only counting the code generation part of the backend and not counting the linker, then we're about 40 times faster. And those numbers make more sense to me these are more along the lines of what I would expect. So I'm happy to report that. Now, as I mentioned before, for many reasons, one of which is performance, another of which we're going to talk about today, we eventually want to get rid of this dependency on the linker down here. You know, the reason we list without link is because we plan eventually to not have to link, at least on our backend. LLVM probably always has to go through a linker, but we will not have to go through a linker eventually. So this 0.03 seconds will not be far off from how long it takes to actually compile the whole program, or the whole backend. Right, this is not counting the front end, which again was about 0.18 seconds. All right, I'm rat-holing too much on this thing that's an old topic, but if you want more details on this, go look at the previous demo. We went into it at great length. All right, let's go into some functionality. I've got a demo, so I put up a link for this static if demo. It's called static if, but there's a bunch of stuff including static if. So go ahead and take a look at that if you have it. Maybe if you don't have it, someone in chat can link the files. So I'm just going to compile it right now. We're not going to pay too much attention to this output for now. We'll look at it later. But I'm going to run the program. And as we often do, it's a bunch of print statements. And then we're going to look at the source code that's generating these and talk about what it's doing. So let's do that. So like I said, we're going to start by talking about some smaller features to begin with. The first one is hex floats, right, which is a way of putting in a floating point number that is concise and exact. So you can say exactly what the bits are in the floating point number. Now, some languages have hex float formats, and they're trying to be you know, portable in some way, or like general or computer science-y. And so they tend to be really confusing formats that are hard to understand. Our hex float format is just the IEEE 754 floating point bits for the number, right? So you say 0H, H means hex float. If I had an editor that did better highlighting for this language, this number would be maybe more readable because the 0H would be drawn thinner, or you know, bolded versus not bolded or something, but you know, so it sort of runs together with the number here, but you know. The nice thing about this format of hex float is also you can, it sort of lends you some understanding about the number. So, you know, let's look at the float 64s, because those have a cleaner alignment between, you know, if you've looked at these at all, you know that there's sort of three sections of an IEEE floating point number. There's the exponent and the sign bit, and then the mantissa, right? And the sign bit's at the very top bit, and then the exponent is these next bits, and then the mantissa is these, right? So you can see, just looking at these hex floats, like, oh, infinity and negative infinity have a 0 mantissa, right? And float 64 max has all 1 bits in the mantissa. So this actually clarifies certain things, which is nice. Now, why would you use this? Well, often when you're doing low-level programming, you have reasons to want to make floating point numbers with very specific bit combinations to help in conversions, or you know, weird rounding that you want to do, or just initializing constants in certain ways, like whatever, right? And so you can do that very straightforwardly now. So these are actually, I pulled from our math library the actual definitions of these limits. This is what we actually use now. Oh, and then I print these out so you can see that these actually work. Now, the way we print floating point numbers is not super robust right now, and we don't print in scientific notation yet like libc does. I'm not sure if we want to do that by default. It's unclear. So you can see, so float 32 min, it looks like 0, but then we compare it against 0 to make sure it's actually greater, and that's true. So this is float 32 min. It's got that 1 bit set. in the exponent. Float 32 max is this really big number, which is actually correct if you check it. Yeah. All right. So now, one thing that some newer programming languages have been doing to help with numeric literals is let you put underscores in them for readability, and so I've done that as well. It was a very easy feature. It took like 2 minutes. But so once you start having big constants, in 64-bit programs, you start having bigger constants flying around than you ever did in 32-bit or 16-bit code. So this becomes more important as time goes on. So here I've got a constant that's 10 million. Here's the old style. And here I've just written it with some underscores in there, right? And so what happens is if we start parsing a numeric literal, we just ignore underscores. So here I'm just going to print both of them, or I'm printing 10 million B, actually. And then I'm printing that A is equal to B, which better be true, and so I am. So the one with underscores is just the same 10 million, and A is equal to B, right? Okay. This also helps with a hex number, especially a big hex number. So I mentioned before that in this 0h case, it kind of runs together with the number. I could have done this, but we hadn't talked about underscores yet. But here's one with the standard 0x notation that's just like in C. This is a 64-bit float number, so if I were to write it without the underscores, right, it would be like this. And if it didn't have such ordered digits, it might be confusing which part of the number is which. So you can see that this is a lot more readable than this is. So anyway, so again, we just print the number. We're printing it in hex and then in decimal. And you can see that it's 1, 2, 3, 4, 5, 6, 7, 8, 9 through F, and there's the decimal version, right? So that's no surprise. And here's just another example, taking those float 64s from above. We're using the underscore to delimit after the 0h, and then after the exponent, right? It's harder to do with 32-bit floats because the exponent only takes the top bit of this digit, and then the mantissa is the rest. So there's not necessarily, if you put the underscore there, you've got like 1 bit of exponent after the underscore, but you might still choose to do that. But I picked float 64 for this example because it's clean, right? So sign bit plus exponent and then mantissa really helps with readability. Now we just eat all the underscores out of the constant, so you could abuse that and do something ugly like this. Just don't do that, right? But just to show that that works, we print out many, and it's, where is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, right? This is float 64 max. Big number, not very much precision. So yeah, so this works. I don't know why you would do that unless you run an obfuscated programming competition. Why don't I disallow multiple consecutive underscores? Because you might have a real reason to do that. Like maybe you want to do, let's go back to this, right? Maybe you have a bunch of, maybe you have a bunch of big hex numbers and you care a lot about the difference between the first 8 bits and the second 8 bits, and you want to do that, right? But maybe that's not readable enough and you want to do that. That's much more readable. Or actually, maybe you want to do that, right? If the point is, that's a lot more readable if you care about the top 32 bits and the bottom 32 bits. So the point is just, like, why would you outlaw it if it can be used effectively, right? So hopefully that answers that question. It's not my job to decide how many underscores you should use. It's my job to make the compiler good. All right. So let's talk about foreign procedures. For the rest of this, so those two things were more like lexical analysis features or something, right? Like small syntactic things. The theme of everything from here on till the end of the demo is going to be dealing with stuff that happens as your programs get bigger and you start to have to interface with libraries and think about naming and name collisions and stuff like that. Okay, so the first thing that we're going to talk about is procedures. They're called foreign procedures here, but procedures, that are in libraries somewhere. So you're linking against somebody's precompiled library, and then you've got just a declaration that says, oh, here's the specification of this function so we can type check it, but it's located in a precompiled library, right? This is very common in C and C++, less common here, but we still do it so that you can interface with external things. Now, the way that has worked the whole time is that there's this, foreign library or foreign system library directive that tells you where things are. And then when you declared a procedure, you would say, let me find a clean one, a shorter, I don't know. So time begin period, you used to just say, oh, it's foreign. You wouldn't give it a body, and then it would look it up in a library. And the way that we worked until now is just like C and C++, which is actually a kind of a broken model. What C and C++ do, and many other languages, because they sort of inherit that model through the tool chain of a linker and stuff, when you include a header file for some library in C, the compiler doesn't really know that the declarations in that header correspond to the particular library that you're using. They just go in a bag, and you shake the bag up, and then at link time you try to refer the names to all these libraries that you're piling together, right? And who knows for any particular procedure which library it's supposed to go with, right? Which A, makes linking slower because you don't know where to look for the symbol, but B, invites problems with symbol collisions, right? Because what if multiple libraries declare a particular symbol? How do you know where that symbol goes? Well, there's not really any good reason for that. It's just that that's how C did it in the frickin' 1970s, right? It's 50 years later, almost. We should probably get better about some of those things. It's one of those things you don't care about until it bites you, and then it's really, really annoying because there's no way to fix it. So the way this works is anytime you include a library in your program, you can bind that to an identifier, and then when you say that something's foreign, you can say in which library it is. So the library is actually a data type. It's only a data type you can use at compile time, right? It's not a runtime thing, but so here's some Win32 API things like get standard handle, close handle, get last error, and I say, oh, they're foreign and they're located in kernel 32, right? And so now we just know where to find those things, and we'll complain if we don't find them in that particular library. So these things are in user 32, etc. So the other thing this does is it documents your dependencies better, which is nice. You can start searching through source code for your dependencies as opposed to whipping out weird binary tools and trying to understand stuff. All right. So that's relatively minor, but good. It encourages clarity and lack of ambiguity. So now another thing that was that I ignored right when we were looking at that is I've got these scope directives here, which control whether things are going to go into file scope and static or global scope. File scope is a new thing in the language, but it's just like stuff that you know from C or C++. So let's talk about that. In C, for example, if you have a declaration in a file, well, it's a little bit complicated, right? Because there's sort of two maybe I shouldn't use C as an example, because there's sort of, if you say something is static and it's in a file, it's definitely way in the file scope. But if you don't declare it, I don't know. Okay, so in C anyway, things are in a file scope by default, and the way that you share things among files in C is by putting an extern symbol into a different file's file scope, right? So there's no, it's not a hierarchical situation necessarily, unless compilers might have implementation details that are hierarchical, but in general, the way that you share symbols is you have a bunch of file scopes. So in C or C++, you sort of just have this bottom row of red boxes, one for each file, and then they just have cross-links to each other, okay? In this language, up until now, there was no such thing as a file scope actually at all. There was only this global scope, and everybody went into the global scope, right? So if you weren't in like a sub namespace in a struct or something, then you could easily have a name conflict with somebody else, and that's not really tenable in the long term, right? Other things about it, though, are very convenient. Like if there isn't file scope, if everybody just goes into the global scope, then you don't have any of these worries about how do you get files to talk to each other, right? Anyway, so, but in order to deal with increasing program sizes, what we've done is we've made a sort of a hierarchical situation where we have both things now. So we have a scope for every file that gets loaded. This could also be module scope eventually when we add one or two more module handling primitives. Right now we sort of have modules, but they're all like in one file. Every file is a separate module. That won't be true later. Anyway, we have this file scopes, and then we also have a global scope that's sort of hierarchically set up as the parent of the file scope. And so here's how name resolution works. It's just like in any other programming language. We're just being clear about the exact structure here. So I've got some procedure called init game. It's in some particular file. So these are 3 different files, say, right? Here's the file with init game. We're looking at the definition of this procedure. It defines its own variable. It compares some variable mode, which it's not defining, so it must be global. And then it says, draw a message, which is also some procedure that must be global, right? So what happens when I'm down here and I see this identifier message? What do? Well, we're down in this scope of this if, that's this bottom block, or no. Okay, when I'm looking up anything, say I'm looking up this procedure draw message, right? Because that's defined globally, let's use that. So first we look in the block of this if, and it's like, oh, that has this variable message defined because it's declared there, but no draw message. So let's go to the parent, right? The parent is like this procedure scope, and that's got name defined, okay, but that's not draw message. So let's go to the parent of that, which ends up being in this file scope, which has init game defined, but we still don't have draw message. So let's go to the global scope, and that's where we find draw message, which was defined in this other file, right? So the file scopes define all their own stuff, but then they export things into the global scope, right? And then we have directives to control that exporting process. And you'll see why it works this way. This might sound a little bit abstract, but hopefully as we go through examples, you'll see why this works this way. Anyway, the way this works in practice is, say I'm loading some file that's got this program text on the lower right, and that's here. That file has declarations of A, B, and C, and it can use all of them, right? So I can say C is B, and that's fine because I can see B or whatever. But in terms of exporting to the rest of the program, I can say scope file here, and that says B is sort of private to just my file, right? And then I scope export, and C is not private. So this is kind of like a private keyword in some languages, or like static in C, but like static has other implications that this doesn't necessarily have. It's just a way of, it's the particular way of namespace hygiene that we're using here. Now you could imagine wanting to like push and pop the scoping state or whatever, and I don't do that right now. We might do that eventually. I didn't want to incur like extra indentation when you do this because, if you do something like extern C or like namespace in C++, it's always a pain in the butt how you have to open a scope and everything gets indented. So I just did this very like, preprocessor style. Although this is not a preprocessor operation, it's a semantic operation. Preprocessor style, just like say what the scope is. Okay, so all that is just to say that here, remember how I declared these identifiers for these libraries. The rest of the program doesn't need to know these, right? This is just for my own file. So I can declare which libraries the things are in, right? Other people might use different identifiers for these same libraries, and we don't want to pollute their namespace, right? So a more typical version of this, let's say, here's a very minimal hash table struct. It's not that fancy. It only stores void pointers with integer keys or signed 64-bit keys. Here's sort of our interface to it. Here's the struct. Everybody can see that. Here's the add and the find procedures. Everybody can see those. Then we go into file scope, and all our private data structures and stuff are down here in file scope. So we don't need to have separate header files and non-header files. Right, we don't need to tag every procedure as private or public. We just do a global directive. So again, that's not, this is not supposed to be like amazing, right? This is the kind of thing that every language has in some way. I'm just sort of explaining the way that it works here. Is that all I wanted to say about that? Yeah. Oh, the other thing I wanted to say is, you know, often when you add something like this, the default is to say, oh, you want hygiene, so the default should be like private or file scope. And that's actually not the way it is. The default is like public or export scope, so things get exported into your parent scope. And the reason I did that is just almost always you want to export some things because that's how you communicate with the rest of the program. And so forcing you to add a directive in order to do the thing that you obviously want to do felt bad. In fact, the first thing I did was file scope by default, and it felt bad. So things are exported by default from your module or from your file, and you only add file scope directives when you want namespace hygiene. All right, 30-second break. I got to get more water. Now we're going to get to the cool part, the fun part. I drink a lot of water when I talk. Sorry, you got to stay hydrated. It's true. All right, so here's the fun part. And this part's about library usage and what happens when you're using a lot of libraries, many of which you didn't write or most of which you didn't write. And the general philosophy in this language is that the main program, right, my program that I'm writing, should control how I see somebody else's library, right? They don't control that, I control it. And this is very different from the way it works in C and C++, where the library itself has to sort of control how you see it. And so I have some very specific examples historically that I want to call on, right? So let's start with an example. So one day, many years ago, I was programming for a console that we will call the Nintendo game block, so as not to incriminate anybody. And it was supposed to be a fun, fast project where I had some game engine code, and there was a game developer who was like, we've been doing 2D games and we want to start doing 3D games. And we want to do a game on the Nintendo game block, so why don't you come in and get your code working on the game block and then license it to us and we'll get started with that. And I was like, cool, that sounds great. I've never worked on the Nintendo game block before. So I'll just bring this tens of thousands of lines of code that I've already written in and like port it and get it working. And in 3D programming back then, as today, we have this thing called a quaternion, which is how you rotate things. And of course, I had a quaternion in my engine because that's how I drew geometry. But of course, the Nintendo game block was trying to provide good high-level functionality in its own graphics library, so they had a quaternion. And they also called theirs quaternion with a capital Q, exactly the same as me. So we had an example of a name conflict. And so here I'm going to look at the Nintendo game block lib on the left. It's copyrighted by Nintendo, so be careful what you do with it. But here they have a quaternion, and here I have a quaternion, and let me get these lined up. So they're very similar, but they actually make different assumptions. So they're not even memory compatible. So my quaternion goes X, Y, Z, and then W in memory, and theirs goes W, X, Y, Z, because they want to go alphabetically, right? Of course, they provide methods to operate on their various, to do various things to a quaternion, right? So you could find the length of it, and for the purposes of this demo, I've instrumented these with, print statements so you can tell which one is happening at any given time. So, here I'm finding the length. This is just a normal 4-dimensional vector length here, and we're returning it. Here we're normalizing it by finding the length and then dividing by the length. Now, here's another way in which our implementations are not compatible. We have a length and a normalize as well. Our length is basically the same thing as theirs. We'll print that it's ours and not theirs when we do it. But our normalize is different because ours is simpler. Ours just finds the length and divides by the length, but Nintendo decided that they want a convention. So if you use quaternions at all, you know that there's a sort of double cover thing where you can multiply a quaternion by -1, and it's the same thing geometrically as one where it's not multiplied by -1, right? And so you might want to rectify it under certain conditions. So here when they normalize, they're also rectifying it by, if the W coordinate is less than 0, then they're going to multiply it by -1 by negating this factor down here that they're dividing by, right? And so that means that after you call normalize, if it's a Nintendo quaternion, the W coordinate will always be positive. For our quaternion, that's not necessarily true. The W coordinate will be whatever sign it was when you started. And those kind of things matter sometimes, right? And so it's important to know which of these we're dealing with and what the conventions are, right? So the problem back then was a little bit intractable because I was doing this in C++, and there just wasn't a good way to deal with it. Like, if you try to put a namespace around the include when you're trying to include the Nintendo library, then the name mangling all changes, and then none of those procedures are found in the precompiled library, right? And that's no good. So you can't namespace it. So I had to basically rename every quaternion in my game engine to a my quaternion, which made me really upset. Because it's just kind of offensive. Like, why does the library get to force me to change my names, right? So instead, we changed the library's names. So here's the new feature. Whenever you do a load or an import, so we also have an import directive, which imports modules, but modules are sort of installed in the system modules folder. But here, for this source distribution, we've just got this Nintendo game block lib as a regular file, so we're just using load. But other than that, load and import are the same. When you load a file, you can add an expression after the quoted file name that is a compile time execution thing. And what happens is let's go back to this diagram for a second. When things get imported from file scope to global scope, the default is they get imported with the same name, right? But what this is a renamer procedure so that when things get imported into your scope, you can map those names to a new name. So here I've done a thing called myGameBlockRenamer. So whenever I import things from the Nintendo game block lib, I look at the name, and if it's quaternion, then I call it Nintendo quaternion, right? Otherwise, I just call it the same name as whatever it was. So this is just like a little shim that I'm inserting into this load to fix my namespace collision problem that was happening. Now, there's other ways you could fix it. For example, And we might enable some of these later as well, like you might load this into a sub namespace if you had namespaces that weren't as screwed up as C++'s, right? And then import everything but that. But I wanted to provide a very general programmatic way of doing this and a very powerful way of doing this. So we're doing it this way, and we're gonna have fun with it during this demo and do a bunch of things with it. The other thing, now if you've seen the previous demos, you know that we have a sort of a compile time metaprogramming facility where you can introspect your program and do all sorts of operations on it. That's also a place where you might want to do something like this, and I may add a way to do it from there as well. But I wanted to make this so simple to use that people like to use it, because there's some things about the culture of naming that I want to change that I think are kind of broken in C and C++, and we'll get into that in a minute. Anyway, let's demo this. So basically all that's happening is anything in this file, so this file, I don't modify this file, right? So this entire source file stays as it is, which is important because it might not even be readable to me. Maybe I'm even, or it might not be writable. Maybe I'm even getting it over the network. Someone's asked a question. That is a good question because we'll get to it in a little bit. Anyway, so all of this source code stays the same. So for example, length in Nintendo's code refers to this as a quaternion, and it's a Nintendo quaternion. But in my program, I can refer to things as a quaternion, and they're my quaternion. And those things live side by side, right? So here's an example. Whoops, I don't use this constant anymore. Never mind that. So I make a quaternion, Q, and it's mine, right? So I set the x coordinate to 1 and the w coordinate to -1, and the other things are zeros, right? And I'm printing that. Here's our quaternion. Whoops, where's my? So I'm printing that here, and there's no surprise. We get x is 1, w is -1. The rest are zeros. All right, so I'm going to make a Nintendo quaternion. Let's go back and look at to Nintendo again. You know, that's just doing this component-wise assignment, but remember their quaternion has things in different places in memory than ours. So, you know, it's not exactly a totally trivial conversion. People are asking good questions, but yes, we'll show the answers to all these in a bit. Like I said, we're going to have fun with it. So we call to Nintendo, and that gives us a Nintendo quaternion. So n is of actually type, n is of type Nintendo quaternion, or that's the name in global scope, right? And it's still quaternion in this scope. So we're going to print out, first we're going to print that quaternion, and then we're going to print the length of it. And remember how we had that print statement. So we should see that when we call length of n, that it's a Nintendo length and not our length, right? And so what's actually happened is, remember that we only changed the name of this. So everything else in this file didn't get renamed. So now length is in our global scope called length, right? And we have a length in our that's defined by us that's also in the global scope called length. And even though textually they both take quaternions, these are different types, right? This is a Nintendo quaternion, this is our quaternion. So these get combined in the global namespace into overloads, right? So length is overloaded in the global namespace once for the type that's our quaternion and once for the type that's Nintendo quaternion, right? So, so then we're just calling length here on Nintendo's quaternion, and then we're going to call it on our quaternion. And the point is, here we had better say Nintendo length and Nintendo normalize, and here we better say our length and our normalize. And you'll see, in fact, that that works. So Nintendo finding length, oh, it's 1.4142, etc. Nintendo normalizing, okay, here's the new coordinates. Note that they're lower. And then we find the length, and it's 1. And those are all Nintendo's procedures, or non-Nintendo's procedures. And, you know, I have this little speech impediment where sometimes I say non as nin. It's just a weird accent that I have. So then here's our quaternion, and note again that the coordinates are in a different order, right? So theirs are w, x, y, z, and ours are x, y, z, w. So we're finding the length, and this is our finding length now, but we get, of course, the same answer as we should. This is our normalization, and we get a shorter quaternion that's of unit length, but note, remember, that Nintendo's normalization, or non-Tendo's normalization, also rectifies the quaternion, right? So in their case, they have a positive w coordinate and a negative x. And in our case, we have a negative w coordinate and a positive x because we started with a negative w and a positive x. So that's just to show that this importation has successfully worked. We renamed their data structure. We solved our namespace conflict problem. And without having to do something tedious like go into the non-Tendo namespace to use everything, or having to rename our quaternion throughout our entire game engine. Okay. Whoops. So that was that. So now let's look at some more uses. Can't type today. Let's look at some more uses of this. So someone was asking in the stream, can you decide that you don't want any declarations at all? Or can you decide to refuse an import? Yes, you can. And the way you do that is just by returning the empty string from your processing thing. So let's look at another example. Here on the left, we've got this thing called mathlib. Actually, I'll go full screen with it for a second. This is a very trivial math library that provides two pieces of functionality. Multiply add operation, right, that multiplies f times a and then adds b, and a square then negate, which squares f and then negates the result, right? So why would you really want to do that? I don't know, but pretend this is like a fast Fourier transform library or something, right? And the author of this library has provided two parallel sets of routines, one for float and one for double, which is, he's an old C guy, so he's calling float 64 double. I'm not going to blame him for that. And so here the code is exactly the same, but you might imagine that the code actually might be different in some way or another that's important, right? Maybe the double versions, if they're iterating, they need to have more iterations or use a different iteration strategy because it's more optimal or whatever, right? There's all sorts of reasons why you might provide two implementations for different data types. But that's what this library does. But I don't want the double ones. I'm making a game and I only want the float ones, okay? So, well, actually, so here, actually, let's look at what we're using first. So we're going to use both of them. So we're saying float multiply add, 1 times 2 plus 3, and then square then negate a, and then we get, 1 times 2 plus 3 is 5, and then square negate of that is minus 25, right? Then here we're doing the same thing with doubles, and we get the same result. We're printing them to the same precision, but these are floats and these are doubles. Okay. Now, suppose we don't want the doubles, we just want the floats in our namespace. What do we do? I'm going to reject them by name. So I'm going to say, here's my procedure called float versions only, and it looks at the name, and it says, if the name starts with the string double, return the empty string, which means reject this entry, don't import it, right? Otherwise, return the name. So now let's turn that on. So right now, note, let's go actually compile again. So we compile successfully right now. If I turn this on, because I'm calling these double versions down here, if I fail to import those, then, I shouldn't compile. So here we're saying float versions only, and we try to compile, and it says, oh, it's an undeclared identifier, double multiply add. And it's like, oh, well, we better import that one, I guess. Or stop using it. So here I'm going to stop using it, and now we compile again. So that's just to say that's a thing you can do. So this code here is just our helper function that tells us when a string begins with another string, right? That's something that you would define probably elsewhere and would be standard. Okay, so here's another example. in the C and C++ world, you have libraries like OpenGL that prefix, they get around this kind of naming conflict problem by putting a prefix on everything, right? So if we go to GL, you'll see, all the procedures are like GL enable, GL disable, GL gen textures, whatever. Everything starts with GL. And the reason they do that is so that if you have some procedure called flush, that it doesn't conflict with GL's procedure flush. That's fine if you only use 1 or 2 libraries, right? But if you use 15 libraries and they all use that convention, then you've got all these little acronyms flying around, and it's hard to recognize them. And B, it doesn't really solve the problem. It just kicks the can down the road, because people are going to start using the same prefixes accidentally anyway, because everyone wants to use 1 or 2 or maybe 3-letter prefixes, and those are finite, right? So you want to solve this problem for real. But before we get to solving the problem for real, let's go back to the philosophy of this language, which is that I should decide, the user of the library, should decide how I see it, not you, right? So GL shouldn't spec that everything starts with GL. If I want it to start with GL, I should spec that, right? And there's good reasons for that I'll show you in a little bit. But for now, here we're going to use a library called Wiz, which is a widget library, the Wiz widget library. And we're going to add have a prefixer on the load that for every name in the library puts WL on the front of the name. So it's like GL, but it's WL. Someone's asking, this is relevant, can you inspect the parameters right now to decide which functions to include? I have not done that at this time. Right now I only give you the name, but if there's use for that, like if you want to know the type specification of the declaration, we actually could pass that as a second parameter, and then you could do all the stuff that we showed in the type info demo and the polymorphism demos and all that. But I'm not doing that yet because I wanted to focus on the namespace aspect part of it. But yeah, in principle, there's nothing stopping us from looking at type information or any of that stuff. I just don't pass it yet. Anyway. So we want to prefix everything in this library. Let's go look at the library for a second so we know what we're talking about. So it's a widget library, so it's got some widgets like sliders and buttons. So it defines this struct called slider, and it's not prefixed, right? So the guy writing this library gets to just call it slider and create slider and destroy. He gets to have nice names for his own procedures as opposed to having to prefix them with weird prefixes, right? So we have some utilities about how we manipulate sliders. We maybe set the name of the slider and set the value of it. We might increment or decrement the value of the slider, and we might draw the slider, right? So it's this fine widget set that lets us manipulate a slider. And let's actually look at the output. Let's run the program again. So here we go. There's an example of rendered sliders. So what we do is we've prefixed all of this, so we're going to call WL create slider, right? Because even though it was create slider here, I've decided I want to prefix it with WL. So we do that. We set the name to fun, we set the value to 5, and we draw it, and then we increment the value, and then we draw it again. So that's why here's a one with value 5, right? 0, 1, 2, 3, 4, 5, right here. And we draw it, and then we've incremented it, and we draw it again. So this fine slider library has done a good job for us. And then we destroy it, right? Now, again, this prefix might we might want to use the prefix sometimes and not other times. Like if we're in a file whose only job is to talk to the Wiz library, then we might find our code a lot more readable if we just drop the prefix, right? But then if we're somewhere else in the program and we want to talk to Wiz a little bit, it might make sense to have the prefix, not only to avoid naming conflicts, but because it's self-documenting, right, a little bit. So there's a trade-off. Like at some point, a little bit of prefix is self-documenting, a lot is noise. at some point, right? And so this is to give you the option to do both. So anyway, so the fact that you see this means that all this prefixing worked correctly. Let's talk about versioning now. Here's another reason why prefixing is not that great of an idea. Maybe there's different versions of the library, and the guy who writes the Wiz library isn't going to change his prefix every time he releases a version, but we might need to interoperate with two different versions of the library, right? So for example, we might have a big game engine, and we're trying to add some UI screens that need to use the awesome new features of Wiz 2.3, but we don't want to have to rewrite all our old code, and some of that still uses Wiz 1.0, right? Or maybe we're even interfacing with someone else's library that we only have a binary of and we can't modify, and they need to talk to Wiz 1.0 to do their stuff, right? But we need to talk to Wiz 2.3. So there are real world, oh, you know, I forgot to point this out before I go too far. Somebody asked this explicitly as a question, and this was in comments, and I sort of flew by it, but you know, in most of the cases, we've been just using an identifier here. Let me actually just recompile and show that this works before we go on. So I've been using an identifier, but really, you know, it's any expression that evaluates to a procedure of the correct type. So here, remember we have this quick lambda thing. So instead of defining prefixer as this procedure, we can make it polymorphic, and the polymorphism will get resolved correctly, right? So we still see our fun slider. So remember, this is a polymorphic procedure. I could type out the whole long form of it, but you know, this is x is of some type t and returns the type of this expression and blah, blah, blah. So that works, but the whole reason for quick lambda is so you can just say stuff straight up, right? So instead of saying load with all that, we can just say load wiz10 and then a very fast map x to concatenate wl with x, right? And that'll do the same thing. Let's compile that. Boom. Whoops. I left off the dot. I don't know why I did that. All right. Wait, what? What did I do? Oh, sorry. Okay. We have an LLVM backend bug that gives us a multiply defined symbol like 1 out of every 100 compiles. It's on the to fix list. Anyway, it works if we don't hit that bug. There we go. So yeah, so you can get this nice short notation or whatever, right? Quick lambda, identifier, however you want to do it, you can do it. Anyway, so we're back to the versioning example, and we're using that syntax here where we're going to load Wiz 1.0, and we're going to prefix everything with W10 underscore, and we're going to load 2.3 and prefix everything with W23, and because we've got different sets of names for those, we can use them simultaneously, right? So I'm going to make a slider in Wiz 2.3, but I'm also going to make a slider in Wiz 1.0. And we're going to set the name in 2.3 to wow and the 1.0 to G. Let's just look at that and see that those work. See? Now the wow actually is much more fancy. See, instead of the straight lines and the vertical line, it has little curly lines and a star. And that's because the amazing features of Wiz 2.3 let us customize the look of our slider. And that's valuable functionality that we want to use, but we don't want to have to we don't have time before shipping this next patch to go back and like replace all the Wiz 1.0 code, which is why we want to leave other screens of our program in the old UI, right? And so we want to use both of these libraries simultaneously. Here we're using the valuable features of Wiz 2.3 to set the display format for our slider widget. So we set the line character and the pip character. And then we draw that guy, and we increment it and draw it again, right? Just like we were doing before. So we have there, wow, and we increment wow and draw it again. And then we destroy it, right? And then we're going to do the same stuff with our 1.0 slider that's more boring and old looking. We're going to draw it, increment, draw it, and then destroy it. There. Now, let's do one more thing and look at the differences between these libraries, right? This is going to be important. So all the names for things are the same. So they both have a slider. This is what's naturally going to happen as a library gets revised, right? People aren't going to change the names, right? Your slider is still going to be called slider. But here we've optimized the display. So the old busted Wiz 1.0 library had this large buffer of 100 bytes that it used to sort of configure the display, what a slider would look like. And that was done by this procedure update slider data, which you then had to call anytime you made a change. So create slider had to call update slider data, and set value had to call update slider value, and increment had to call update slider data. And then the draw procedure would just draw what's in the slider data, right? Well, that's fine, but in the new Wiz 2.3 library, it's more immediate mode where there is no slider data, right? But we've got these extra members line and pip character that control how we display. And our draw routine down here actually dynamically computes the image of the slider without pre-configured data, right? Using very sophisticated algorithms, but it requires no storage, so that's great, right? So that's just illustrating why we would want to use the new fancy library. Okay, what was this one called? Versioning. So one other way you could do it if you had namespaces that were better than C++'s namespaces is you could just import the versions of the library into different sub namespaces, which is something that might work, I don't know, like in OCaml or something. I don't know, but you probably can do that in that kind of language, right? And we'll probably make that work as well. We're about a hair's breadth from that working right now. But also my feeling is in languages where it's the tradition to have to dereference a namespace to call things, it's just a little bit of a pain in the butt. It's just a little bit sucky. Maybe that'll be true here, maybe it won't. But I want the ability to pull stuff into your own namespace and have it feel like yours and have a great deal of control over it, which is why I'm making sure that this facility is good. All right, so this next example is just to show that when you import things with different names, they're still the same thing globally. And by the same thing, I mean sort of the same library or file, right? So let's say one part of your program wants to, let's go to a blank file for a second. Let's say one part of your program wants to use networking. So you might load network, and we're not doing anything prefixing here, right? And let's say a totally different file wants to do something with networking. You might also load it like that, right? You want these to be the same thing. You want to be able to treat these files as different units. Like maybe I can drop them in and out of my program, so they each declare their dependency that they need network. Oh, somebody asked a question that reminded me I forgot something. Yes, we'll go back to that. Hold on. We finished this point. Two totally different files might declare that they need this library, and you want that to refer to the same instance of the library by default, right? If this thing has global data structures, you want those to be the same global data structure. If it has multiple procedures, you want it to be the same, right? You don't want to recompile all those procedures. And that's just to say that the default behavior here, whether you prefix things or not, is to get that same behavior. So in this example, we've got another library called Security Bank, and it's got some global state. It's got some secure encryption vault. That's a global variable, right? It's one of these vaults. And it's got some methods for creating and setting the secure key and transacting. And transact here is just printing a message with the secure key. So going back here, we're going to make two vaults called A and B. And here we're using the unprefixed version. So here, by the way, we've done this weird thing of loading the same library twice, once without prefixes and once with prefix. Now, we're showing, first of all, that that just works. But secondly, this is something that might just happen when multiple parts of your program import things. This might just organically happen, and so we're demonstrating that they refer to the same code and the same data. So here I've got 2 vaults, and I'm using them. I'm creating them unprefixed, and I'm going to release them and set the secure keys to dead beef and cafe food. And we're going to make B current and transact, and we're going to make A current and transact, and make B current and transact. And you've seen our output. B is current, cafe food is the secure key when we say hello, and then A is current, and the key is dead beef, and we say sailor, and then B is current, and we say Odysseus. So you see the global state is switching back and forth as we switch between these guys. So now we're doing the same thing, but with the prefixes, and we're going to start by getting the current global vault and putting that in old vault. We're going to set something to new vault and transact. Actually down here. Okay, wait. So we get the old vault. We create a new vault, but we're going to transact on the old vault first using SB transact. So I'm saying prefix, which is just to say I'm calling transact with this SB prefix. So we're going to transact actually on the old vault with the prefix function, and it's just to show that these are the same functions in data, right? And then I'm going to make the new vault current and transact, and then make the old vault current and transact. And the fact that we can do that, and here I'm not going to go through it, but look, it just worked, right? The fact that we can do that shows that we are sharing data and procedures. They're not different instances, right? So we can release the new vault, the address of the current vault, and SB current vault. Remember, so current vault was this global variable, but we've imported it twice, once with its regular name and once with the name SB current vault. And those are actually the same variable. So we've made an alias for it effectively with 2 different names. So you can see that here, they have the same address. These are also the same types. The vault and the SB vault are the same type despite being imported with different names. However, this reminds me that I forgot, somebody asked this question, which is good. These 2 different libraries are different types, right? They're not the same library, so they have different declarations for things. And so if you try to use this, remember going back to the Wiz widget libraries, we were using Wiz 1.0 and Wiz 2.3. If we try to destroy a Wiz 2.3 widget with Wiz 1.0, that should be a mistake that the compiler catches, and it is, just through the normal type checking mechanism, right? However, we get more detail in the error message because the types are the same in the files, right? So we said, hey, you're trying to call destroy with incompatible structs. We wanted something called slider, and you gave us something called slider, but actually the slider that we wanted was bound to W10 slider globally, and it was in this file wiz10.jai, right? And we were given a file from a slider. It's called slider in file 2.3, but it's bound to W23 slider globally. So the compiler, in cases where you have a type mismatch, but they're defined to be the same name in the file, it goes the extra mile and searches the namespace to find what the binding is that you're actually using to give you a more helpful error message. This is a long error message, so we might actually be even more helpful if we can shorten it somehow, but that is what happens, right? So that's good. But in this case, because it's the same library, the types are the same, and there's no problem. However, sometimes you might not want it to be the same library. You might want different instances of the same library. So, let's talk about that for a second. Why would you want to do that? Well, let's talk about it from the library author's perspective. Often I'll write some code, and like this security bank file, it just makes sense for there to be some global data. There's like either a global variable or a global buffer of data that we're going to send to the GPU or something, right? And in cases where there's only ever one instance of this code running, that's fine. You don't have a problem with the global data, right? I mean, provided that you've worked out all your threading, synchronization, and whatnot. And you'd rather write the code just with global variables because it's simpler, it's easier, right? Now there's this weird idea that programmers seem to have lately that started maybe with the object-oriented thing or maybe earlier, that that global data is bad in all cases and you should always put things in objects and whatever. But the problem with that is that sometimes functionally, all you really want is a global piece of state, right? And if you're pretending that it's not global by like wrapping it in all this stuff, then you're making your code bigger and possibly slower, and you're making it more annoying to use because like now people have to allocate something that's really a global, right? So if you want simpler, more bug-free code, then when something is global state, you should actually let it be global state. Now the problem with that is often there can be rare cases where somebody might want to have more than one instance of your thing, like maybe they want to thread it in a certain way, or maybe they want to have multiple concurrent activities happening in their program, and each activity requires a separate global state, which is what we'll show in a second. Now in those cases, in a language like C or C++, you're out of luck in most cases if you have global state. You could do something tricky, like maybe on Windows, if it's in a DLL, you can create multiple instances of the DLL, but that's a pain in the butt, and it gets into very platform-specific stuff that you would rather not have to muck with, right? You'd rather just be able to do it. So when you load a library, you have this, or your own source file, right? It doesn't have to be an external library. You have this directive unshared that says, mount this as a separate instance, effectively. Recompile the whole thing as a separate instance with its own data, right? And in this case, so that we don't get name conflicts, I'm mapping each of these instances to a different prefix. So the I means isolated. I just mean that they have different global states. So I'm going to make a security bank starting with I1, one starting with I2, and one starting with I3, right? So here I'm just going to demonstrate that that all works. So I'm going to make 3 vaults. One is in I1, one is in I2, one is in I3. And I'm creating them all as separate, 3 separate vaults. I'm not using any of them yet. I'm not deleting them yet, right? We're deferring that we're going to release them later. That's all good. Now, one thing that you might imagine happening is like, oh my God, you have all these things laying around. How do you keep them straight, right? What if you make a vault from I1 and you try to set the secure key using the I2 API? Is that going to break? And in this case, actually, you'll get a compile time error. Because these are unshared, they're separate state and separate procedures, and the compiler knows that. And so it'll generate the same kind of error that we got before, right? So here it's like, okay, you tried to use a struct. Okay, you tried to call I2 set secure key, and that procedure wants a struct that's bound to I2 vault globally, but you gave it something bound to I1 vault globally, right? So, and the same if we try to call I3 release, that's super bad. Like if that uses the heap and it's a separate heap or something, you'd be in trouble if you did that, but of course we catch that, right? So this gives you type safety by default. If you want to override the type safety, you can, because these types are memory compatible, right? Because you just loaded the same code 3 times. So you can cast them explicitly. If you want to cast your I1 vault to I3, probably not recommended, but if you had to, you can. Okay, so now we're going to call I1 make current, I2 make current, and I3 make current. So now we have 3 separate global states. All from what, remember, there's only one source file. There's only this source file, right? We've just loaded it 3 times. We didn't have to do some ugly, like in C, if you were going to make this work, you might have to do some ugly preprocessor thing throughout the entire file where you define a prefix. And then that prefix is on everything, and you would be like prefix underscore double double what, and that's on like every damn thing in your file, and that gets ugly real fast. And plus, yeah, it's annoying. We don't have to do that. We just import it. So, oh, sorry, I'm skipping over stuff. So we make all three current, and then while all three are current, we're going to do a transaction on each one. So we're going to do an alpha transaction, a beta transaction, and a gamma transaction. And we should see each of those with different secure keys, which is just showing that the different global state is being kept sort of in parallel in all three of these modules. And if we run, you'll see that's happening. So here's alpha with 3 different keys and 3 different vault names, beta with those same 3 keys, and gamma with those same 3 keys. So all this state is being kept and organized very well and very nicely from one tiny code snippet that we have reloaded 3 times. And the point of this, again, is to sort of reduce this bureaucracy and over-objectification that people do just in case, right? So I can write my code just to use global variables, and I don't have to worry, like, what if somebody wants to use this multiple times? Because the language will let them use it multiple times on their own if they want to. I don't have to make the code more bureaucratic in order to enable that, right? And it's nice. It makes me feel good about my own code, right? If I want to thread it, say I write some code and I haven't thought about the fact that a global variable will be a race condition if multiple threads mess with it. I just wanted to write it as a global. Well, that's fine. You can import it into its own namespace per thread if you want. Now, of course, the way we've demoed it here, you have to give it an explicit name, which sort of limits what you can do. You couldn't like dynamically allocate 1,000,000 of them probably unless you named them all. But there will be ways around that in the future as well. This is sort of showing the first step. So you don't have to take all these weird precautionary infrastructure measures that you have to in something like C++. People can put that infrastructure in themselves, and that infrastructure will work the way they want it to, not the way that you thought maybe it might. And that's better because you can't predict everybody's needs or desires. They know how they want things. You don't exactly know. So, yeah. Is that the last? So unshared. Oh, we've got a whole static if demo. Okay. I'm going to take a short couple-minute break and refill my water, and we'll talk about static if when I get back. Okay, saving my voice. I got to get better at speaking. All right, so the last feature we will demo is static if. Yeah, a lot of people are seeing flickering. Sorry, it's just how it is. Twitch or OBS or something is, yeah. All right. Let's talk about static if. Okay, so prior, Someone's asking, is this functionality coming out of real problems you're encountering with your current game? Some of it, yes. I've already been having namespace conflicts and stuff. But some of it is more about problems I've had historically with other software. So it's all coming from real problems. It's I would say with the current game, I'm not using enough libraries yet. I'm using maybe, if you don't count Windows system libraries, I'm using maybe 4 libraries, which isn't really enough to start running into these problems. Like when you start using like 20 libraries, yeah, it becomes an issue. All right, so static if. Prior to this demo, we didn't really have a way to do, for example, operating system specific inclusion of files or code or whatever, and you need to do that as a matter of practical fact. Actually, when I say you couldn't do it, you certainly could do it. You could do it in the same way that C or C++ does, which is use a preprocessor to preprocess your text and blah, blah, blah. But I didn't want to do it that way. I wanted to do something that's more of a semantic operation, right? Why is that? Well, for many reasons, but you know what? I've got a comment later where I enumerate the reasons. Let's just take for granted now that this is something that you that you think is interesting. So here, let's just look at a couple examples. So I'm using static if at top level. The way you do it is just hash if. Again, this is not a preprocessor if like it is in C. This is a directive that's doing things at semantic time. So by the time this runs, the code has been parsed, and anything in the condition of this if has been type checked, and based on, and then it gets statically evaluated. So this OS Windows variable gets looked up, and if it evaluates to true, we load this file, otherwise we load this file. So what happens is directives like load or system library or something activate at semantic time. Okay. Let me just show, let's get concrete as soon as we can here. So I have these files, demo static if Windows, right? And it says calling OS dependent routine for Windows, right? It's just got an implementation of this procedure, OS dependent routine. And let's go into the Linux version. Same thing. It defines the same procedure, it's just for Linux instead of for Windows. Very common thing that you might want to do all the time, right? So I'm just saying, well, load one file or the other, right? Now, yeah, let's just keep going because I don't want to be redundant, and I explain some of this stuff better later. So here you see that I called the correct one, right? I call here OS dependent routine right there. And you see that we called the one for Windows. Now, let's start getting into why you would want to do it this way instead of with a preprocessor. And there's lots of good reasons. I'll go in the order of the comments. So one reason is so that your code doesn't rot as easily. So I just said that, you know, based on which branch of this that you're in, you know, we either this load happens or this load happens, right? But both of these get parsed, right? So one thing that happens to me a lot of the time is I'll like search and replace a variable, but I'm using the old name of the variable, or maybe I delete something, but I'm still using it in some branch of the code that is getting pre-processed out because those conditions aren't set. And I won't discover that that's a problem until like 2 weeks later, or somebody else on the team who's using that build sends me a message really annoyed saying like, oh, you broke the build because of blah, 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 right? So let me just demonstrate that if I put some stuff here that, whoops, that doesn't parse, right? That clearly doesn't parse. When I try to compile, it complains about it, right? Even if So I started this by talking about identifiers. That's not quite right, because identifiers won't get caught here. So if I say, but parse errors will. So weird search and replace errors and stuff will get caught. The reason we don't catch identifiers, I'll show you in a minute. It's quite intentional. Anyway, so the point is, if you introduce this bizarre error in this block, we actually catch it, even though we're not actually executing this branch of the code, we're executing this branch, right? So your code is a little bit more robust against rotting. Now, in this example, you can start to see a hint of why we don't chase down identifiers. Is actually, well, this is a library, and if we're on Windows, this library exists. But if we're on Linux, it's some other weird library that doesn't exist on Windows, so we don't actually want to look up that library, right? Well, a similar thing happens with APIs and whatever. So say we're going to render, we might want to do something like this if down here, where let's say we call this bake me procedure with true if we're on Windows, or false if we're on Linux. Then if we call it with true, we just want to print X is true. If we call it with false, we want to do some Linux thing with some identifier that's obviously not declared, right? Now this is correct syntax, so we're checking the syntax, but the semantics of this is unknown because we won't know the semantics unless we're compiling for Linux, and so we don't want to actually resolve this identifier, right? And so this just gets ignored essentially once it parses. Let me go back and show, I don't want to beat this too much into the ground, but let's compile. Whoops, I didn't save since I took that out. Okay, so we still compile. Now, if I introduce a syntax error here, this is a little different because it's at imperative scope rather than like the global data scope like we were up there. But again, we'll get a parse error. We got several in a row, actually. But we don't get an error for the missing identifier, and the reason is because you might declare that identifier when you're in Linux, right? So we're checking syntactically, but not semantically. Okay. Now recall that this is our auto bake syntax, and why it's double $sign or double $sign, and what that means you can all see from the polymorphism demo from way back. But what that means is anytime we call this procedure, we have to know the value of the argument lexically. Like it has to be known at compile time. And because it has to be known at compile time, then in the body of this procedure, we can treat it as constant. So we can do these conditional things, right, that you couldn't do in a preprocessor. Right? So in a preprocessor, you don't know if you're calling bake me with false or true, right? But we can use a static if to definitely include or definitely not include code, right? So as opposed to, so let's talk about if it was a regular, no, we'll talk about that in a bit. Let's just blast through. So here's another example. We have y, it's a constant, it's 5. And we're running a more complex thing. We're saying if factorial of y is greater than 100. So this actually automatically gets farmed off into a run directive that executes this result and gets passed back to the if. So if the factorial of 5 is bigger than 100, which it is, it's 120, we say big factorial. Otherwise, we do this undefined thing, right? Which again, this is an identifier that is not declared. And so of course we compile and we run and we got a big factorial, right? And if we change that constant to something small, then we'll get an undeclared identifier, right? Because this code is not even executing, right? Or it's not even being semantically evaluated, right? It's not being type checked. The identifiers are not being resolved, right? So now, so the first thing I'm going to do is call bake me with false, right? Because we know this is false, then we can evaluate these ifs, and we're going to hit, again, these undeclared identifiers, right? That's no surprise. The other thing is, if I try to change this to a regular if, so the whole reason this is a static if with the hash mark here is so that we can do stuff like this. We can have undeclared identifiers, And it's fine, because those identifiers mean something in a different configuration, right? If we change this to a regular if, then it's going to complain that this is undefined, because regular if, it could go down either branch, and even if you could statically analyze that this goes down the first branch, right, which you could in this case, probably, it's the compiler's sort of job to make sure the code in the other branch is at least well formed or whatever, right? So that's the thing, is regular if requires all your code in both branches to be compiled, and the whole point of static if is that you don't compile half of them, right? Or you don't compile whichever branch of the if is false. Okay. Now, again, and what's interesting about this is because it's not in the preprocessor, then the calling site determines the evaluation of this if, which doesn't happen if it's a preprocessor thing. All right, so now this also works, in other scopes like in structs and whatever. So here we have a hash table, which is a struct. We're parameterizing the hash table on some type of what's the value that we're going to store in it, and we've got this array of 100 of those values. And then we're going to do something special, like if this happens to be a string hash table, we might want to do something particular, and we're going to represent that in this case. We're not going to really implement a hash table, but we're going to represent that by saying, well, there's some string field that has hello sailor in it, whatever. That you might, instead set the hash function or some additional data or whatever. If the value type is not a string, then just put some other member that's in -99. So we're going to make a float hash table and a string hash table, and we're going to print those, right? And so you see, let's recompile again. Hopefully I fixed it. Yeah. So you see, here we've got X. It's a hash table that's got an array of 100 floats, and it's got that something else member. And then Y is a hash table that's got an array of 100 strings and that hello sailor member, right? So those are now different structs with different members, configured very easily at use time. And also it's very easy to use the static if to determine which one that you want as the person defining the data structure. Now we had a way to do this before that we've demoed before, which is to use the body text directive. Okay, so I'm going to scroll down here to this example. It's the same thing. Let's just look at the output. The output is the same thing. It's, it gives us the same results for each data type. But the difference is, body text right now, you have to supply the text for the whole body of the struct, first of all. That might be fixable later. But so the issue right now is, I have to redundantly put this member both times. So it's a little noisier here. Depending, it may be feasible to later on make body text more modular so that you could get rid of that kind of thing and just put a member here and then do body text. Maybe. There may be unforeseen issues with that I haven't thought about, but that'll probably happen, right? But the other thing about the body text method is that the code that you're inserting is in a string, which means it can't be introspected very well, either by you or external systems. So your own code browsing, right? We've demoed code browsing and stuff in previous demos. You can look over the syntax tree of your whole program through your compile time metaprogram. That code browsing can see into both bodies of this if, both the true branch and the false branch, right? Because it's not in a preprocessor, that code hasn't been erased or eliminated, right? And it's not in a string, so it's not like cryptic in some way. It's there in the syntax tree, so you can see it directly, right? In the body text way, well, it's very versatile because you can put together what string you want, but your metaprogram has no way to introspect it. Similarly, your editor has no way to introspect it, right? You see here, this is in Emacs, which is trying to do syntax highlighting and formatting. And here, it's doing syntax highlighting and formatting because it can see the code, because it's just in this if. Here it's in a string, so it's all blue. It's like Emacs doesn't know what that is. Even though it's just code, it's not getting the special treatment that code should get, right? So that's another advantage that you get from using something like static if for this kind of simple case, right? Now, if you have a very, very involved case where the string is very complicated to build, you may want to use body text, and that's all fine as well, right? So we're not deprecating body text, we're adding an additional facility. All right. Now this gets a little bit into nitty-gritty details, but this if gets evaluated anytime that we build a new struct for a polymorphic struct. And for a procedure, it gets evaluated anytime we build a new procedure, which means it'll run a limited number of times. It won't run every time I make a thinger of some so here's a struct thinger that just takes some argument type. And we're going to abuse the if to have the clause that we evaluate be a print, which is where all these print thingers are coming. Remember, okay, here, let me just clear. When we compile, remember we had all these thingers? That's where this is coming from. We're abusing the static if to do a compile time print, which is a little weird, but I wanted to do it for the purposes of illustration here. So we start, we have a thinger of float. We're declaring A to be a thinger of float, right? And so that's this one, right? And we've got a thinger of int, and that's this one. And we've got a thinger of thinger. So this is the first funny thing. Thinger is an abstract type, right? You can't instantiate a thinger without an argument. So a thinger of float is a specific type, and a thinger of int is a specific type. But thinger by itself is not a type that you can instantiate, but it is a type that you can talk about in the type system, right? In the compile time type system. And we've demonstrated that before, but this one is funny because I can make a thinger of thinger, so it's a complete type containing an incomplete type, and because we don't instantiate a variable of that type, we're fine. We can actually print that it's a thinger of thinger, right? So we're kind of reasoning about what it is, as long as we don't have to instantiate it. If I try to instantiate D as a thinger without an argument, of course that will complain. This is all kind of old, right? We're missing the argument. But I just wanted to show that that's still there. We can also make a thinger of this very involved type of 957 pointers to arrays of thingers of strings, right? This is much more readable than your equivalent C++ template type, by the way. And you can see that it's a thinger of 957 whatevers, right? Now, here we make a redundant thinger of float and thinger of int, but you note that our printouts stop here. We don't have another thinger of float and a thinger of int, and that's because we already made those. So this if, in the same way that you sort of, if you include a module multiple times, you probably want it to be the same module. If you instantiate a thinger of float multiple times, you want it to be the same data structure, right? And so we only generate that data structure once. So that's just an illustration of that. I'm not sure how much you care about that in actual real world use, and you probably don't want to abuse if this way, but I'm abusing it, right? So that was the version for structs. Here's the same for procedures. So here's this procedure, takes an argument x, it's of some type t, and we just print that we're instantiating that. And so here again, we get it for string, float, boolean, int, but only once. We don't get it twice, even though we're doing it twice, right? And the reason is, again, because we only instantiate this procedure 4 times, and then the other 4 times is reuse of the same precompiled procedures. And then we're just showing that, this does all the obvious things that you would expect, like you can nest them and all that stuff. So if we're on Windows, print Windows, which we do. Let's go back there. Oh wait, I cleared the screen. So if we're on Windows, we print Windows, which we do. Here we have constants alpha and beta. If alpha is greater than beta, we print that alpha is better, which it is, bigger, which it is. And then we get a random number, which is a runtime or a compile time execution operation, and see if the low bit is set. And if it is, we say bonus, and if it's not, we say no bonus, and it's no bonus, right? So it's just to say that you can use this in all these good ways. Wow, the demo's taken a long time. It's been a long time since we had a long demo. So I'm going to take a couple minute voice break, and we will be back for questions. thanks for everybody sitting through the main demo. I feel like previous demos were more exciting, like compile time execution and stuff. But the fact that we're getting down to this more like work-a-day problem solving, like naming conflicts, and we're still able to solve it in a powerful and, to me, kind of cool way, I think is good for two reasons. One is that because the size of the features are getting smaller, means we're starting to converge on the final language design a little bit. And two, it just means that the problems that I'm having are getting smaller, right? Which means that problems are getting solved. So yeah, that's good. I'm gonna take a 10-minute voice break. Q&A at 3:55 p.m. PST.